or delta x equals negative m over k times a. We have a displacement is directly proportional to the acceleration. Over here, we have an angle that is directly proportional to the angular acceleration. We can go through the same arguments as we did over there, but in the end, this is like Hooke's law. I have position or displacement is equal to negative m over k times a. So we have it in pretty much that form. So the simple pendulum will obey Hooke's law to a certain extent. Again, as long as theta starts out small. If that's the case, then the period of a simple pendulum would be 2 pi times the square root of, well, instead of m over k, m translates to L, k goes to G, so square root of L over G. Historically, this is actually an incredibly important equation. First off, the mass does not matter, the actual mass itself. Supposedly, Galileo figured this out while sitting in church and looking at the chandelier swing. If I know what the acceleration due to gravity is, and I know the length of the pendulum, I can create a period. So let's figure out what the period is for 1 second. If I want a period of 1 second, what does L need to be? So the period I want to be 1 second, and that's going to be equal to 2 times pi times the square root of L over, we'll just stick with generic 9.8. So doing the fancy math, I got 1 over 2 pi squared equals L over 9.8. So L 9.8 times divided by 4 pi squared. If someone would be kind enough. Tremendous amount of faith that they're having in you, Logan.
Always do. Maybe I should mess up some. These being radians, right?
No, they're
Oh, right, we're just 0.2482.
units.
Meters per second squared? Or no, meters.
Yeah, meters. It's a length. All right, so about 25 centimeters. So that's roughly from there to there. So if I have a pendulum with roughly with a radius or a length of that, then my period is 1 second. So that means it takes 1 second for, if I pull it out at a small angle, let go, it's going to go there and back in 1 second. Which means I now have timing down to a ½ second. So if it gets to here, that's a ½ second. Matter of fact, I can do timing down to a quarter of a second, because it'll take a quarter of a second to get there, another quarter, another quarter, another quarter. So I can now start doing timing. If I lower L, I lower my period, and I potentially can have even higher, more precision in my timing. And so I can start to do experimentations with smaller and smaller times. Let's see how well it works. All right, so we need to figure out what that distance is, and still no meter stick in here. All right, there are enough times I want a meter stick that I'm just gonna let that run, and I'm gonna go grab the meter stick. All right, so the length that we need to pick, the assumption is that we're dealing with a point mass, and this is not exactly a point mass. It has some size to it. So I want to go to the center of mass there, which I'm going to assume is roughly halfway. And then the pivot point is probably midway along this bar, if this, yeah, that's loose enough. And so we're talking, it would be helpful if I did it this way. So 39 point, looks like 39.7 centimeters. G, let's assume that we're gonna nail this one. 9.798 meters per second squared. So we can now plug in, calculate the period for this specific example. 2 pi times the square root of 0.397 divided by 9.798. What do we get for the period?
.263.
Yeah.
Got that? And looks like you did not get that.
1.2647.
2647.
Yeah.
Oh, I rounded. I don't know why I rounded down. I rounded down instead of rounding up. I saw 47. I went to 2.647.
1.2647?
Yes.
Okay.
I don't know why I saw the 7 and went.
I technically got 1.265, but.
Here's 1.265, all right. Well, in terms of our precision, I doubt if we'll be able to distinguish between those two in timing. All right, so we're gonna do time it, so get out your stopwatches. And we're gonna do,
I got what she got.
what?
I got what.
You got what you got? Okay. So, well, fortunately, that rounds that.
Yeah.
I saw the 47 and instead of going to 5, I went down to.
Yeah, sometimes when I'm trying to think of what the date is, I put down 1989. It's my go-to. If in doubt, it's 1989.
Is that a good year for you?
I got married that year, so I guess history is still gonna decide if that was a good year or not. So far, so good. Yeah, I'm still with my first wife.
That's good.
All right. So I'm gonna pull it back. So a small angle, something like that. All right, I'm gonna do 1, 2, 3, go. When I say go, I'm gonna let go. And then we'll time 10 oscillations. Here we go. 1, 2, 3, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
12.47.
12.47.
12.54.
12.07.
12.50.
Now, as much as I would like to throw out the 12.07, probably shouldn't.
I did it on beat.
You did on what?
Like I did on beat, I didn't wait for you to say 10. I did.
Ah.
You said 10.
Okay. If we average those up, that 12 point something. So that's.
Perfect.
Okay.
Yeah.
That's for 10 oscillations, so for one oscillation, we have 1.2395 seconds. We're off by, if we round off here to 1.240, then we're off by 5%. Not bad. Now, in terms of science, just dropping out the times that would be inconvenient. If we drop that out, we'd have a better percentage. However, not legitimate. You can, if you're going to want to throw something out, you can throw out the smallest and the largest one. So we could throw those out with some legitimacy. However, and businesses have ways of excluding the outliers. All right, so there seems to be some, hopefully you see that there's some legitimacy to this. Questions up to here? So now, let's talk about waves. We've been doing some of the math behind it. Let's get into a little bit more of the vocabulary. We've talked about frequency, amplitude, period, wavelength. Let's get into the actual propagation of waves. In essence, there are three types of waves, two of which are pertinent to this course, one of which is the next one. There are longitudinal waves. And there are transverse. These are mechanical waves. That was horrible. That's the word mechanical. The mechanical waves require something in order to propagate it. They require a medium. I'm going to leave a little gap there. And then there's the electromagnetic wave. That's a topic for 152.
Heard a lot about those.
Say it again.
Heard a lot about those.
Well, you're bombarded by them constantly.
Mm-hmm.
Now, one of the reasons I put a gap here is one, to separate the 151 content from the 152 content, But there is sometimes another wave that textbooks will throw in, and at this point, I think most textbooks do leave it out. There is another type of mechanical wave called the surface wave. And the surface wave is just a combination of those two. So that's one of the reasons why textbooks leave them out. So let's talk about what distinguishes transverse from longitudinal. And the slinky is here. I have a slinky. It's not just bragging, it's leading up to what we're doing next. Hopefully get them to stop wiggling as much. What I'm gonna do is I'm gonna release some coils from up top. What did you notice?
I didn't see anything.
It was moving up and down in the area it could.
Or I guess I should, can you see it there, or would it be better with a white background?
It's,
That first. One person with an opinion? Oh, it's split. All right, we'll do this, we'll do them both then. All right, so I've got the coils right here. I'm gonna release them at the top. Get the, stop wiggling. More. Aaron, what did you see?
I said you can see go all the way up and down.
All the way up and down? Is that what you said? So what you saw was a wave pulse going all the way down to the bottom and all the way back up. I was hoping someone could see that. Against the black background. That was horrible. Hopefully you see something going all the way down, all the way back up. Now the coils themselves, which is the medium in this particular case, the coils are only moving just a little bit. What you actually see go all the way down to the bottom are places where the coils are closer together. So you see these places where there's a compression. So longitudinal waves you're going to have a series of compression and what's called rarefaction. So if we're talking about coils, you get these areas where they're farther apart, areas where they're very close to each other, and then they spread out. So there's a natural distance between them. Coils sort of compress together. This would be compression. Let's assume that this is normal. And this would be rarefaction. So the particles themselves, the coils, all they're moving, in the case of when I had the slinky here, they're moving up and down just a little bit, but you see something go all the way down to the bottom, all the way down to all the way back up. In a longitudinal wave, the particles in the medium, in our case the coils, will move either parallel or anti-parallel to the direction of the wave itself. So the pulse went all the way down, the coils move along that same axis. So longitudinal wave, particles move parallel or anti-parallel to wave. Anti-parallel just means opposite direction. Transverse waves. Someone want to take a guess at how those particles move?
Perpendicular.
Yes. Particles. Wow. We're in a slow one these days. Particles move perpendicular to wave. have you been to a sporting event where they do the wave?
Hmm.
Okay, 3 of you. That is a transverse wave. Because you, as the particle, are just moving up and down. But the wave itself is sweeping around the stadium. Or partway through the stadium, depending on how well it worked. So that's an example of a transverse wave. A couple other examples, the longitudinal wave. Sound is a longitudinal wave. So sound's a longitudinal wave. My vocal cords are basically vibrating back and forth. They're pushing air molecules. And again, I'll say it, I know there's no really such thing as an air molecule. When I say air molecules, I mean molecules that are in what we call air. So my vocal cords are vibrating back and forth, forcing molecules closer to each other. And then when my vocal cords pop back, there's a place where there's much fewer. And so a sound, you can have a bunch of molecules in the air really close to each other, and then they spread out. And then they're really close to each other again. And then they spread out. And so basically that the sound, you'll have this wave or this compression, hit your eardrum, popping it in, followed by rarefied air, which will suck the eardrum back out, and then push in, pull out, and our brains somehow connect that to words. Now, if every